Okay, so let's have a quick look at the script wiring feature of the force operator. If you've watched the third DVD in our series, you may remember that I gave a brief outline of what script wiring can be used for. Let's quickly run over it again here and then have a look at practical examples in action. Each particle can have an extra 4 channels of numbers created for them via MaxScript and a script operator. The 4 channels are integer, float, vector, and matrix. You can only store one integer value in the integer channel, but you can store any float value you wish in the float channel, 3 floats in the vector channel, and 12 floats in the matrix channel. The float channel is the one that concerns us here. This channel can be accessed by the force operator and its value used instead of the normal influence percentage parameter value. This means we can store a float value per particle and then have the value control how much of a force is applied to that particle. To turn on this feature, right-click on the force operator in its event and select Use Wiring. So we'll actually just have a look at that now. You can see in this flow here we've got 3 scripts that actually set up the actual float channel of the particle to work with script wiring. We'll actually turn all of these off first. And if we go down here, we see we've got a force gravity, and if we right click on it, you can see that we've got Use Script Wiring turned on. If you turn on script wiring, I'll actually turn it off so we can see what happens. When you turn it off, you can see you have an extra group here which is missing. So we'll turn it on again, and you can see what the group is. It's called Script Wiring, and it only has 2 options: to use the influence set up by the float channel, or to not use the influence set up by the float channel. That's all you can do with it. You can see if it's not used, it'll use the normal percentage value here, and if it is used, then it'll use the influence value here. And that's actually set up by these scripts here. So, what can we actually do with this float channel? Well, it's possible via various algorithms to work out the volume of our particles, and we could assign this to our particles to simulate mass. Or we could simply assign a random value to our float channel. Or maybe work out another value by using a distance to an object. Let's have a look at our example file and see what these actually do in action. You can see we've got 3 options here. They are script drag, script distance, and script position. And I've actually renamed all of these myself to represent what each one does. If I actually turn on not used and set this to a lower value, let's say 150, and then press play, you'll see that the particles fall down and then eventually collide with the ground plane. As you can see, I've actually scaled the particles so they actually have different sizes. So it would be nice if maybe the larger particles fell faster than the smaller particles, or if we wished it to be the other way around, we can actually make the smaller particles fall faster than the larger particles. Let's say our particles are made of polystyrene, then it may make sense that our smaller particles with less drag would actually fall faster. If they were heavier particles, then it may make more sense that actually the larger particles fell faster. So let's actually see that in action now. If I turn on script drag, this actually sets up the float channel of each one of these particles to have a value based on their volume. And if I go down to the force and actually turn on influence and press play, you'll see that our particles actually fall at different speeds. And you can see the largest particles have the less force applied to them. So as you can see, that's a pretty cool feature. Now in this case, I'm actually modifying the gravity, which is probably not the most realistic thing. Probably the most realistic thing to do would be to actually modify the drag. And in that way, the particles will all have the same gravity applied to them, but some of them would actually have more drag than other ones. If we have a look at the script for that, you can actually see how that's actually worked out. And you can see that we go through the usual script, we set up the number of particles, and we go into a loop. And we say for every particle in the loop, the particle float value equals 10 minus the particle scale times 5. And this basically, this algorithm I actually worked out here, worked out to give me the kind of values that I needed. So in other words, it's working out the size of the particle, and then it's using that to actually work out a float value to put into the channel to actually make script wiring work. If I turn that off and turn on the second one, and we have a look at what this one does, this one says for every particle in our flow, the particle float equals 220 minus the distance between the particle and a target position. Now, In this case, target position is actually the sphere that I've got here. So we're working at the position of this target object, we're working at the position of the sphere, the particle, and we measure the distance between the two, we take it away from a certain number, and that's used to define our float value. So now if I press play, you'll see that particles, that's actually very fast, so let's try and slow that down slightly. If we actually scrub it, it's probably the best way to see it. You can see the particles which are further away from our target object actually fall slower than the ones closest to it. So you can see all the particles very close to it actually fall very, very quickly and then strike the ground plane. Now, if we wanted to change that value, we can actually go in here and we could then, let's put another bracket and then let's divide that number by 10. I'll just evaluate that and press play and see what happens. See now our particles actually fall much slower. And that's because I've actually divided the force value that I was using to define the actual amount of force that's applied. I divided that by 10, so obviously it's 10 times weaker. If I go into that script again and edit it again and let's say make it 100 and now press play, obviously it's 100 times weaker. So now our particles fall very, very, very slowly, as you can see. So that's that one. The next one, this uses the position of the particle. So if I actually edit the script, you'll see what it's doing is it's using the particle's x position and it's just dividing it by 100. And that means particles which actually, this is the center of the world here, so particles which are to the left of the center of the world are actually negative. They're on negative x, and those to the right are on positive x. So in other words, particles to the left will actually have a negative force value being used here, an influence of a negative value, and the ones to the right will actually have a positive one. So the particles to the left get pulled downwards and the particles to the right actually fly upwards. So let's play that now, and there you can see it's in action, and it's actually linear. So you can see the further it goes to the left, the more force is applied to our particles, actually pulling them down, and the more we go to the right, you can see the more force is applied to the particles to make them go up. So these are very simple examples, but they do show you that you have total control by using script wiring over how much force is applied to each particle. And that can actually be applied to multiple forces, but that actually gets quite a bit more complex. And I'll actually cover how to do that in a future DVD. Okay, so that's it for our forces. The next chapter on the DVD is on collisions. You may have actually viewed this already, though, if you actually viewed the DVD in the defined order that I set up. So if that's the case, we'll just head on to the conclusion for this DVD.